start the recording. So hopefully that should be recording. Great. So here we go. So welcome all to the first in the webinar series. This webinar is on the hydraulics of proprietary devices, and thank you so much for coming along and giving up an hour or so of your time in what we know is a busy period for everyone in the industry. Hydraulics is what we deal with every day. It's how our devices function, the flow of the water, and making sure that hydraulics work properly is key to the design of any stormwater system. So this webinar is going to cover a few range of topics. The first one is stormwater treatment in general and the range of devices that we have and how these devices are chosen. Then we're going to select some of representative proprietary treatment devices and look at the treatment mechanisms. So how actually do they operate, and how does the hydraulics affect how they work? We're then going to look at physical drop, the definition of physical drop, the definition of driving head, why offline treatment design is best practice and what the implications have on hydraulics for using offline treatment design. Then we'll look at tailwater and downstream water levels and its effect on specifically StormFilter operations, but others as well. And then a quick summary of designing with proprietary devices and what we look at and what we ask for. So stormwater contaminants, we have to treat stormwater, and that's because there's a broad range of contaminants that come from different sites, different land uses, and we have to make sure that they don't get into the receiving environment. The contaminants themselves can broadly be categorized by their particle size. Oils and hydrocarbons that we generally keep separate, but then you have litter and trash, which is considered everything greater than 5 millimeters. Coarse sediment, which is in the realm of about 110 microns average particle size. Then we've got fine sediment, which is down to anywhere near kind of 20 microns or so. And then dissolved contaminants and nutrients. So for each type of stormwater contaminant, there is a different level of treatment that is required for that. So for example, litter and trash, you want to have 100% trash removal. With coarse sediment, you have pre-treatment, which is typically 50% removal of coarse sediment. For fine sediment, it's typically 80% TSS removal. That's what our devices can achieve, is at least 80% TSS removal, but the standard in New Zealand is 75%. So looking at the standards in New Zealand, then there are guidelines. There are guidelines for Auckland, GDO1, the Christchurch Waterways, Wetlands and Drainage Guide, the Christchurch City Council Infrastructure Standard. Waikato has got the WLAS RITS standard. NZTA has got a stormwater management treatment standard. But none of these are based around hydraulic design of proprietary devices. They go into the details of how to design wetlands, how to design rain gardens, how to design swales, but it's not specific to proprietary devices. And that's quite key because there are differences between these that need to be considered. Now, if we go back to the different levels of treatment, for each level of treatment, instead of having a rain garden design or a specific swale design for a certain level of treatment, we have a range of devices. And a comprehensive line of widely approved BMPs allows you to identify, we need this level of treatment, let's put in this type of device. Different sites have different levels of treatment, and some councils would have considered that as part of an approval process. So some councils will say you have to have an approved underground filter for 75% TSS removal. So let's consider three of the proprietary treatment devices. On the left, you've got the Cascade Separator. That is a gross pollutant trap, and all gross pollutant traps are generally sized for 50% TSS removal with a particle size distribution with a D50 of 75 micron. Then in the middle, we've got a JellyFish. The JellyFish filter is a membrane filtration device that achieves in excess of 75% TSS removal, including very fine particles. And then on the right, we have the StormFilter. The StormFilter is a media filtration device that can be used for both TSS and some metal removal. So at the design stage, we will ask you for the treatment requirements of the site, and that helps us select which device to look for, the catchment areas and the flow rates, both the water quality flow rate and the peak flow rate, and that helps us size the device. We'll ask for the available depth to invert of both the inlet and outlet. We'll ask for driving head constraints and downstream water levels. And the reasons that we ask you for that, rather than just simply saying, here's a device that works, will become clear. So looking at the Cascade uses hydrodynamic separation to achieve 50% TSS removal. Water flows in from one or more inlets and is directed around the central chamber in through two flumes, and then you have two opposing vortices in the central treatment chamber. These two vortices use hydrodynamic separation to settle out fine particles, and floatables get captured on the top. As the water level builds up, as the flows increase, water then flows out over that weir, and then peak flows, there's an additional weir, so peak flows can bypass, but the floatables are held within that central treatment chamber. With a lot of gross pollutant traps, the devices have to be very deep to prevent rescouring of previously settled out media. This skirt equalizes the pressure and allows the sump to be shallower than other treatment devices for the same amount of storage. So we're at roughly, say, 3.5 meters deep versus 4.5 meters or 5 meters deep for other comparable devices. As the water then drains down, there's a permanent water level in the device. The JellyFish, water flows in behind this maintenance access wall, and that builds up to the driving head level of the device. Water is directed down into the bottom of the treatment chamber, where oils and floatables, trash and debris are then captured, and the separation skirt prevents oils and stuff getting trapped in the membrane filter. Water then bubbles up through the filters and then flows out from the device. As the water flows out, you can see there's that central backwash pool, and what that means is as the device then drains down, you kind of have a negative head, and that what that does is that forces water to drain down from the back through these filter cartridges, and that provides an element of self-cleaning. And this drain down cartridge here allows us to equalize the pressure. The StormFilter works as a siphonic treatment action. So what happens? This is a cross section through a StormFilter, one singular cartridge. And what happens is storm flows come in, they fill the cartridge bay, and water flows up under the hood. As water flows up under the hood, air is released out of that one-way valve at the top. Once the water level is at the top of the hood, the float will lift, the ball will then also lift, and that allows water to flow out through the central column into the underdrainer manifold. And at that point, the siphon effect has been activated, pulling water evenly through the very large media area. Once the water starts draining down, then the siphon then breaks. At the point the siphon breaks, then air bubbles come up, and they physically agitate the media. And what that does is that helps agitate media away from, agitate contaminants away from the media and down into the treatment bay. That again provides an element of self-cleaning to the StormFilter, which helps prolong the maintenance, or the period between maintenances. As the water level drops, the float and the ball drops back to the imperfect seal, allowing the remaining water to drain. So with the StormFilter, there's no permanent water level within the device. So this is another cross section through a larger storm filter, showing it no longer in isolation. So water flows in to the treatment chamber, and then the siphon is activated. Water then flows out, and then as flows stop, then the siphon breaks and the balls drop down. With both the JellyFish and the storm filter, there is no limit to the amount that we can scale the devices. With the storm filter, we can run from a single cartridge in a 1050 manhole all the way up to the largest storm filter installation in the Southern Hemisphere is in Christchurch, Bells Creek, which has about 580 cartridges. So regardless of the catchment area size, we can provide a solution for the treatment. So then looking at the hydraulic elements now of how the hydraulic design impacts the performance of the treatment devices. So Kevin, who is our lead technical engineer, he wrote a paper for the Stormwater Conference in Nelson back in 2016, looking at, run through in great detail the considerations and implications of different hydraulic elements on treatment device design, which I will be able to make available after this webinar. So Stormwater360 and most other devices on the market use gravity and water flow to affect the treatment performance. It's only in Christchurch where there are some pumped devices, but even then, that is just to the pumping is not pumping water through the device; it's pumping water to achieve the gravity through the device. So for our devices to function properly, hydraulics are key. And the term head in itself can be a confusing term. The first consideration is physical drop through the device, and this is commonly known as elevation head. Now, physical drop or elevation head is defined as the differential of inlet and outlet inverts across a hydraulic structure. So what does that mean? So if we look at the Cascade, we have the outlet invert and the inlet invert. So there is no physical drop through a Cascade. So if we were to have, say, if we just say that head is the difference between inlet and outlet, in theory, then you'd say that there is no elevation head for a Cascade separator. There's no physical drop through a Cascade. For JellyFish, you have the outlet invert and the inlet invert. The inlet invert on the JellyFish is at standard 150 millimeters above the outlet. So there's the inlet and the outlet. But with the JellyFish, the inlet is on a sliding scale. It's not at a defined point. So anywhere within that range, you can put the inlet and outlet. So there is up to 150 millimeters physical drop through a JellyFish, or you can have a bubble up JellyFish. So that would be where the inlet is lower than the outlet and water bubbles up through the filters. So a really good example of this is a non-trafficked JellyFish. And you can see here that the inlet is typically 150 millimeters above the outlet, but the inlet may vary and it can be installed below the outlet pipe. Storm filter, you have the outlet invert, and the great advantage with the storm filter is there is very minimal depth below outlet invert. So you're not having to dig a larger hole for a sump that sits below the treatment chamber. So the outlet invert and the inlet invert. Now with the inlet invert, there is a range. Typically we say it's 770 mil above the outlet, but that can be anywhere from between 30 mil above the outlet to 770 mil for 69 centimeter cartridges. So again, with a storm filter, there is between 30 mil and 770 mil physical drop through a storm filter manhole. So again, there are options, and we can adjust these options to suit the constraints that there may be on a particular network on your site. So that was elevation head. What is driving head? Driving head, which is also commonly known as hydraulic head, is a measure of the mechanical energy caused by flow. It's defined as the differential of upstream and downstream water surface elevation across a hydraulic structure. Now, if we're applying that to a treatment device, driving head is the water surface elevation required for a treatment device to function. Now, driving head is therefore independent of the physical drop through a device. If you consider a bubble up jellyfish has a negative fall through the device, but you can't have a negative driving head. So let's look at what the driving head means in relation to our devices. So with the Cascade, as we saw in the video, water builds up behind the treatment weir, and so what that means is then you have a driving head that is defined by the height of that treatment weir. However, the driving head also varies based on the device size and the treatment flow rate. If you have more flow going across a weir, you will have greater head losses across that weir. And this shows the minimum driving head for the Cascade. For the jellyfish, so the driving head is shown here on the drawing. And as you saw on the video, water builds up behind the maintenance access wall. And so what that is that then gives us the driving head definition. The driving head is measured from the outlet invert, and that is typically controlled by an upstream weir or overflow baffle within the jellyfish. As standard, the driving head for the jellyfish is 457 millimeters, but we can adjust that down to as little as 150 millimeters if required by site conditions. The cartridge size and the driving head, therefore, independently affect flow rates through the cartridges. But with the jellyfish, the driving head stays the same regardless of the inlet level. So you have the outlet and the inlet range. So that driving head, which is the water surface elevation required for that device to function, is the same regardless of whether that inlet is anywhere on that sliding scale. So again, that's the difference between driving head and physical drop or elevation head through the device. And they're not one and the same thing. With the StormFilter, the driving head is shown here on the drawing. So this is a 69 centimeter cartridge StormFilter, and the driving head is 770 mil. And that is the water surface elevation required within the device for the floats to pop and the siphon action to start. So you can see here, that is the water surface elevation required. For 46 centimeter cartridges, that's reduced to 540 millimeters. And for 30 centimeter cartridges, that's reduced to 380 millimeters. The thing to consider, though, is if you are reducing the driving head and the cartridge size to treat the same flow rate, you will need more cartridges, so the device will expand in footprint. Again, with the StormFilter, the driving head stays the same regardless of the inlet level. So from the outlet invert to the range of the inlet inverts, regardless of the fall through the device, you still have to have that driving head, the water surface elevation within the device, to achieve treatment flows. So if you do not have the same fall through the device as driving head, that does mean that you will have a surcharged pipe upstream. So this is an example taken from the New Jersey Corporation for Advanced Technology, an NJCAT report. So the physical drop between inlet and outlet is 240 millimeters, whereas the driving head at the treatment flow rate is 750 millimeters. So you can see then that you're going to have water surface elevation within the device that is going to surcharge your upstream pipe to be able to achieve the treatment flows through the device. So in relation then to a treatment train, what does that mean? If we're placing devices in series, whether you have a GPT followed by a StormFilter to improve the maintenance period on the StormFilter, there is a driving head on the Cascade, and then a driving head on the StormFilter, and we can't have too much tailwater acting on the Cascade during the treatment performance of the StormFilter. Otherwise, the treatment flows of the Cascade will be compromised. So we've got the driving head of the StormFilter and the Cascade, and then that combines to have a compound driving head, if you like, for a treatment train. Let me look at offline design, and offline design has quite an implication for dealing with peak flows through the devices and hydraulic losses through treatment devices in peak flow events. Offline design means only water quality flows are routed through the treatment chamber, and all other flows in excess of water quality flows bypass the treatment chamber. This is best practice for all stormwater treatment devices, whether that's a stormwater pond, a wetland, or a proprietary device. Within Auckland, all proprietary devices are required to be offline. And this is a little snip from an Auckland Council approval for a proprietary device. It's not a Stormwater360 proprietary device, and it says that the device has to be configured in an offline configuration to ensure that only flows up to the water quality flow are routed through the filter system. So what does that mean? Well, the first option is, if you look here, this is an offline design using an upstream manhole. So we have a manhole upstream that collects all the flows. That manhole has a weir in, and then you have the treatment device. That weir level is set at the driving head level of the treatment device. So if we take a cross-section through that, we have the JellyFish with the upstream manhole with the weir in. So there's the permanent water level in the JellyFish. Flows start to flow into that upstream manhole, and then that builds up to the driving head level of the device, and then any flows in excess of that will overtop the weir, and they'll bypass the treatment system. So if we go back to this design, flows in excess of the water quality flows. So when the device backs up and surcharges up to the level of the bypass weir, flows will then directly bypass the treatment system. With the storm filter, we have the option of providing that within one structure. So instead of having an upstream manhole, we can provide one structure. So we have the bypass chamber with the bypass weir and the treatment chamber. And if we compare that to the offline design with an upstream manhole, you can see here that we are keeping the treatment chamber and the bypass structure separate. For very shallow sites, we've got to consider the head loss across the diversion weir. The geometry of that weir will then obviously affect the head loss of peak flows across that structure. And if the site is very tight, we can design that peak diversion device with this in mind, in consultation with the consultant, obviously. If we pass the peak flows through the treatment chamber without having any form of offline system, the head loss will be higher across through that device. So instead of having a very minor head loss across a bypass weir, we might have a considerably larger head loss for a 10-year event if it's going straight through the treatment device. And that can present issues both in terms of treatment performance and ongoing surcharging the upstream network. Then we look at tailwater. So we've considered surcharging, but now what's happening after the device, and how does what's happening after the device affect the treatment device? So tailwater is defined as the water surface elevation located downstream of a hydraulic structure. And tailwater is an important design consideration for locating a treatment device within a stormwater network, because if it's tailwater could be caused by downstream detention tanks, ponds, or streams. That can affect the performance of the treatment device. So let's take, for example, a storm filter. Storm filter has a driving head, in this case, of 770 mil, and that assumes a free draining outlet pipe. Tailwater, though, reduces the effective driving head of the device. So if there's tailwater, say, from a downstream detention tank, that'll impact onto the device, and then you reduce your effective driving head. So if you have a driving head of 770 mil, your elevation, water surface elevation may have been met to pop the cartridges and start the siphon action, but the driving head will be reduced from 770 mil by whatever the tailwater is. So what are the implications of this? So you will have a reduced treatment flow rate from a reduced effective driving head. The system will prematurely bypass, and you won't treat the full first flush and water quality flows that the device has been sized to treat. If you are designing with tailwater, you may have to accommodate a reduced flow rate per cartridge and thus require more cartridges, and you're more likely to resuspend previously settled material. You can also lead to biofouling, premature clogging of the device, and increased maintenance frequencies. So it's something we like to try and avoid if at all possible. Ideally, we should design so no tailwater acts on the treatment device, but some tailwater in temporary circumstances can be acceptable, providing there's no tailwater during a water quality event. We limit to tailwater conditions to at least a 2-year storm, and there's a drain down time of a few hours. So how can we minimize tailwater? Well, if we take, for example, this cross-section of a catch pit to a storm filter to a detention tank, the discharge invert from the you've got the discharge invert from the detention tank and the driving head level. So as there's water in the detention tank, that acts as tailwater onto the storm filter. So the first option then is to change the tank design. So we can lower the level of the tank, whether you lower the outlet or you change the tank to a shallower tank to reduce the tailwater acting from the tank onto the storm filter. The second option is you can change the storm filter design. So we can minimize the depth to invert by either changing the configuration, lowering the driving head, making it non-trafficable. And as a result, we reduce the impact of tailwater onto the treatment device. So within the range of devices that we've got, there are a number of different options of JellyFish StormFilter Cascade. And for each of those devices, there are a number of different configurations that we have available. So with the design of proprietary devices, most council guidelines don't consider the hydraulic design of proprietary devices as part of their guidelines, and it is kept separate. The distinction between driving head and physical drop, they need to be independently considered. Whether you're retrofitting a treatment device into an existing line, so you'll have minimal drop through the device, you will still have driving head that is in excess of that physical drop. So when you approach us for a design, we will ask you for the treatment requirements, the catchment areas, and the flow rates. We'll ask for the available depth to invert for inlet and outlet. We'll ask for the driving head constraints if there's any structures upstream, and we'll ask for the downstream water levels if there's any detention downstream. And by putting all of that together, we can then, in consultation with us, yourselves, and our engineering team, come to a solution that is going to have positive treatment outcomes and not negatively impact the hydraulics of your treatment design. So that is a quick run through of the driving head, elevation head, and physical drop, and the difference between the two. That's a run through of offline design and tailwater. So now what I'll do is ask if there are any questions that anyone has about anything that we've covered as part of that presentation.
Hi, Matthew. Sorry, I got a little bit late. Are you able to share this presentation afterwards with me?
Yes, so the presentation will be, the recording will be made available afterwards.
Okay, thank you.
Is your explanation of tailwater effectively the same as backwater?
Is our engineering team in this call?
Because I have to admit, I got disrupted for a second when you just started talking about it, and I was trying to figure out if it's basically the same.
I can answer that, Matthew. Yeah, okay. Effectively, yeah, Rose. Is it Rose?
Yeah, yes. Thank you.
Rose, effectively, same sort of term, tailwater, backwater, back pressure or back pressure water. It's basically water coming back into the system.
Copy. Okay, I was just like it was a new flash term or something, so I was like a bit lost.
Yeah, it's challenging with the terms, and this is the reason why Matthew's gone through this training the way he has, because these are common terms that we see day to day. So,
thank you. I'm probably one of the older engineers. That's probably why.
Matthew, if I may just add a comment quickly. So for the engineers that works with designs within Auckland, that section on online versus offline, Matthew said correctly that this is best practice. It is the best way of managing not only your treatment but also your hydraulics. But in Auckland, this is a requirement, and I just want to clarify quickly. So all treatment devices, especially the proprietary treatment devices, must have an internal overflow. So where an offline design with an upstream diversion weir is not necessarily a requirement, let's say in Horizons District, we still need to have an internal overflow within the device, and that's pretty much to prevent your upstream flooding during peak events and those kind of things. In Auckland, it is quite important to distinguish between an internal overflow bypass, which is not really sorry, I shouldn't use the term bypass. I think it's an internal overflow. Let's just get the terminology right on that one. And this is not something that constitutes council's requirement for a bypass of peak flows. You need to have the peak flows. So as that snippet that Matthew showed earlier on, any flows exceeding your design treatment flow rate needs to bypass your treatment section of the system. So it needs to be diverted externally from where your cartridges or your media is sitting. I just want to clarify that, Matthew. Thanks.
Are you guys designing that bypass chamber, or are we doing that? I would have assumed we are.
When you Matthew, you're on mute, so I'm answering at the moment, but I'm going to give it back to you.
I was going to say it does depend, and I'm sorry I missed who asked that question.
That's Rose.
Rose, hello Rose.
Yeah, thanks.
It depends on the arrangement and the project and the scope, I guess. If you adopt this general arrangement, we can that is shared here, whether it's a JellyFish or a StormFilter or a Cascade that's placed offline, we can provide you with the driving head level of the treatment device, and that will then dictate the level that the weir is set at. In terms of the design of the weir, if you want to increase the length of it to reduce the head losses across that structure because of upstream considerations, that's something that I guess we can talk to, but the design of which is left in your hands. But if we're providing you with a peak flow, a peak flow diversion device like a manhole structure, or if we're providing a StormFilter or JellyFish vault that has the peak flow diversion built in, then because we're building that is something that we would then design in consultation with the requirements of the weir and the implications of the hydraulics of the system that you provide us. So, for example, a good example of that is that in the manholes, the weir is at 90 degrees perpendicular to the direction of flow. In our larger devices, in the vault systems, the weir is actually set at 45 degrees to increase the length of the weir and reduce the head losses across that structure. So it's something that can be adjusted as required. We just need to know the information to be able to consider that as part of the process.
Hey, Matthew, yeah, it's Jackson here. Just want to check whether you have a minimum driving head for each of the devices. For our design, I mean, I know the JellyFish doesn't require too much driving head, but obviously we do have to consider the surcharge for the upstream pipe.
Yes, I'm just going to skip back. So the driving head, the driving head of each device will depend on the device configuration that you choose. So with the JellyFish, as standard, the driving head is 457 millimeters, but we can go down to as little as 150 millimeters if required. I mean, the main consideration is the moment you reduce the driving head, as I said, the treatment flow rate per cartridge decreases. So then you would have to have proportionally more cartridges to treat the same flows, so the device gets progressively larger and the cost can increase. So in terms of minimum driving head, I mean the StormFilter has standard driving heads for each cartridge size, each cartridge depth of 770 mil, 540 mil, or in only very tight circumstances would we recommend going to the 30 centimeter cartridges. Generally speaking, we can make most things work with the StormFilter between 69 and 46 centimeters. That driving head is set, but the difference between inlet and outlet is variable. So that's where we can, you know, have 30 millimeters fall through the StormFilter and then surcharge the upstream pipe. Does that answer your question, Jackson?
Yeah. Because I think we had those sort of challenge in the past where we only have like 300 mil height difference between the inlet and outlet. But I think you guys didn't have that 300 mil cartridge at the time. Only had 6946. So we sort of have to have the upstream pipe surcharge, but also we need to make sure that it doesn't surcharge or have any impact on those other connections onto this upstream pipe. So
for particular sites like this, Jackson, where you have 300 millimeters between inlet and outlet, that in itself is not a problem. We regularly design to as little as 30 mil fall through the StormFilter. But of course, we have to then consider the implication of you know, what the water surface elevation within the device and the impact on the upstream network. And that's where, you know, we can work with you guys to review, you know, what our device's impact is going to be on that upstream network design, and if there's going to be any you know, implication of surcharging structures upstream. And we can design the treatment devices with taking into account both upstream and downstream water surface elevations if we need to. So it's not only the fall through the device, it's what's kind of around it and what's upstream and the level of surcharge that's acceptable.
Yeah, definitely. Thanks.
Rose has a question.
So back on the back of what Jackson's just asked, and not sure how other consultants are going on this front, but as we've been in this Auckland Council formats for 11 years, it is getting harder and harder to get practical and pragmatic designs through all the hoops at council. Do you guys get involved council doesn't really like surcharge in their public network. They like everything to gravity discharge and not be holding stormwater for achieving driving force. Do you guys ever get involved in those debates where we know it's going to work and we're not going to surcharge manholes out into the road or anything like that?
Faden, I'll let you talk to.
Are we on our own still with that fight?
No, Rose. You know, I think one of the advantages that we have as a technology company is that we need to know the requirements that we're working to and that we're designing to and that our R&D processes are aiming at. So we engage with the councils that we operate and supply in, and obviously Auckland Council being one of the major ones. We are constantly in some kind of process of engagement with them. We don't always see eye to eye. Is that diplomatic enough, Matt?
Yes,
so.
That's ultimately diplomatic.
Okay, but yeah. So there are requirements from them that we don't always agree with, but we do work with them quite often. Rose, what I'm saying to you is that we are not in a position to influence, but we are in a position to educate, especially based off the international learnings from the company, our experience in the field that is ample across the country. So we can draw on a lot of information and experience, not only locally but internationally as well. So, and I think the councils have started to realize and accept that. It is difficult from a perspective where one can see us or choose to see us as a technology partner, but you can also see us as just another supplier. So it is a bit of a fine line to walk sometimes, but we do engage, I think, quite actively with Auckland Council. We had a session with some of their senior specialists yesterday out in the field to show them some of the technologies on how it operates and how the maintenance impacts. But then back to your question on design guidance and specific compliance requirements or consent conditions, we don't influence, but we do educate. You are welcome to tap into our team's knowledge and experience. If you get a pushback from council, we won't be able to act on your behalf, but we will definitely see if we have some resources that we can provide you with, which is a quick and easy resolution to what you need, and to push back to council. Ideally, you know, I think part of this type of session is also to fortify engineering consultants with the correct information, the correct type of terminology, standardize some of these issues, and that gives us a consistent push on council where we think that a specific requirement may be unreasonable. Yeah, so I don't think I'm answering you to what you want, but
that's cool. And the other thing would be, are you guys willing to? I mean, if we're batting in on something that they're not happy about, are you willing to let us know of? Because once something's consented, it's public knowledge, and you'd have good knowledge of where all your devices are. So if we are pushing the boundaries and you've already had something approved, it's always helpful for you to let us know that where those devices are, so that we can say to council, well, actually, you've already approved that.
Yes, absolutely. I think one of the big struggles with council is sometimes consistency, and that varies sometimes by the temperature of the day and sometimes by the person that you speak to. It's not always great, but you know, there's a reason for the structure that they put out. I think one of our major concerns at the moment is the transparency of what they always, you know, we always get a surprise on something new. So yes, we will definitely be able to assist you with any information that is within our power to provide you with, without obviously trying to influence anything from our side. But yeah, no, absolutely.
And to add to that, I think councils are understanding that a lot of the time we're not trying to be confrontational about asking these questions. A lot of the time, certainly with my dealings down in Waikato, it's a case of, well, we have this opinion. We want to understand your opinion so we can make sure that we're offering the right solution to the consultants, so there's not then the disconnect between what the consultants have been told by Stormwater360 and what council is expecting. And I think that's, you know, really key, is we're approaching all of this is to try and work towards a common solution of better water quality outcomes. And it's just the process of getting there can sometimes be challenging, but yeah, you know, we're able to help, and we're having these conversations anyway. So for sure.
So if you're based down in the Waikato, that's a much easier kettle of fish than Auckland. You don't even get danger money for that role.
Yeah, their regional council is quite good to deal with. But you know, I live in Auckland, so and we still do plenty of work up here. So
Rose, just I think the last point from my side is that where a specific consideration or issue that you have on a pushback from council on a specific design element, where this is a more global matter, we do take it on as part of our direct engagement with council. So it's not that we won't. An example would be this online versus offline requirement. Now, while we understand this quite clearly from a technology perspective and the limitations that our product approvals are bound by, or you know, maybe the conditions of use is a better term. Anything that touches that is grey in the market or in the sector is something that we fight heavily with council to clarify. There's you know, there was a pushback recently from a consultant to say, well, the offline configuration of a proprietary treatment device is not clearly defined nor transparently provided to the sector. And it was a reference to the Stormwater Code of Practice. And in a sense, that is a council concern. So in this case, we are pushing hard, and we're setting up a meeting with council. It will be within the next couple of days to discuss how this information can be made available to consulting engineers so that it is clear. There's no gray areas. The exact requirement is understood by everybody, and this information is transparently available to everyone, and where that's going to be, because it is quite critical, and it does cause issues in the sector. There's another new thing that popped up, is where you have, for instance, a wash bay, where typically one would have used a diversion system, where you would have your wash water with all the detergents and all that connect to your sewer or your wash water or your waste line, and your stormwater would then be overflowing from that diversion system. After all the dirty water has been diverted to the waste line, your stormwater would overflow into the stormwater pipe, and that would be fine. And the new requirement from council is that you now also have to treat the expected clean stormwater coming from this wash pad, when there's no washing activity, which we are considering in one of our approaches to council on, how far do you push your treatment requirements, and whether this is a overkill or whether actually they've got a point and this is a necessity. So there is active engagement, and we will take up the more global design matters with them. Our concern is still the best environmental outcomes always, and where this has been touched, we will step in.
Natalie has a question.
Hey, can you hear me?
Yep.
Cool. Sorry, just in case I missed it, but you talked about the driving head, and obviously that head is important for the performance of the device, but is there a tolerance there in terms of maximum driving head that negatively affects the performance of the device?
The driving head itself, I guess, is a fixed point that the device operates at. For take for example the StormFilter, that is the level at which the device functions at. Anything in excess of that, you will have more water going through the filters than what they're designed for. I mean, yes, you can increase the driving head of a StormFilter, but you will force the water through quicker. There won't be the same contact time with the media, so you won't get the treatment performance, and it's outside, I guess, the design parameters of what that is. So with the StormFilter, we try and avoid that. Same with the JellyFish. We'll design the JellyFish with a particular driving head, and then the bypass structure will accommodate to the water surface elevation within that device to stay at that point. The Cascade is a bit different because you've got it's not a defined point because it uses hydrodynamic separation. You can put more water through that device for a faster to treat more water, but to get a verified and certified treatment performance, there will be a maximum treatment flow rate, but you can then put more through that if you need to. So I mean, we try and avoid using too much driving head through a device, because then it kind of pulls it outside of how it's been designed to operate. There. Does that answer your question, Natalie?
Yeah, mostly. I guess I was just wondering, is there a small tolerance there in level? Like I'm only talking like 50 mils or something like that.
Yeah, I guess that's
probably within reason, sort of thing. Within
reason, and that would be in that kind of situation. Then we would pass that over to Matthew Murdoch and Kevin to review, to see, and that depends on upstream factors and other stuff as well.
Cool,
Matt, I've got a comment. Hey, Natalie, how are you?
Hey, how are you?
Good to hear you. Listen, so in some cases, and it seems like there's a question of pushing more treatment flow rate through a device. Is that correct? Than what we would.
Yeah, and I guess it's probably just I guess an example could be, I mean, you could look at all these examples, but say differently, kind of a Filtera device where you have a ponding depth.
Yeah.
If you start to exceed that ponding depth, what's the tolerance until you're starting to negatively affect that device?
Yeah, I think Matthew's comments are all valid. On a particular example, if we use the Filtera device or a biofiltration device with a ponding depth, what you'll have is we can design. So I mean, you're well aware of our design team, and you're well familiar with the guys in the team. So we will typically look at that, and we have done designs where we have had to increase the flow through the device, and that is a custom design that we typically do. In that case, and I'm going to take a StormFilter as a quick example. So for a very constricted site owned by Kainora, we couldn't increase the size of the manhole for a specific StormFilter, a specific size, just because tree roots, services, and all that. Well, we have a lot of reasons. So what we had to do is, that is the maximum size we had available, but the treatment flow rate exceeded what we would consider the treatment flow rate for each of those cartridges. In this case, what we had to do is to increase the overflow baffle in this device. So, and that allows the increased flow rate through the device. So what you'll have is the device will still operate, but you will have less contact time with your media, for instance. And the only implication on this one would be your treatment performance. Now, on a biofiltration device where you increase the bonding depth, Kevin, thanks for joining. You can add on to this, but where you increase the bonding depth by design, yes, can be done. There's a couple of practical implications on that, but I think the most important one is, once again, you will have increased conductivity through the media because you have more, water pressure pressing down, hydraulic pressure pressing down through the media, which means that you are once again losing a bit of treatment performance. And in that case, if we have some flexibility, we will try then to compensate for that with a bit of an increased footprint or something like that. But that is something typically, Kevin, that you guys would take from a design perspective. Kevin, did you hear the question?
Yes, I did. The treatment system itself, when if you need to put it through, if there is a higher head put through this treatment system, it will not damage it in any way. There is where the overflow is set at that point where it starts going over. So it will be treating at the same time as it will be overflowing as well. Even if you put through 100, 200 mil, let's say, in a StormFilter or JellyFish above to what is designed, it will not damage the system at all. But at that point, there will be some overflowing through the overflow weir. So it will start discharging. I guess it will start releasing some of the contaminant that got captured. But more than that, an example of with the Filtera system, you may put an additional 200, 300 head on top. It will not really damage it. But at that point, I would be more concerned about the velocity coming through it, that it might be scarring the media or the mulch on top.
Yep. Okay. Cool. That answers that.
Great. Well, look, it's come pretty much to the end of the hour. Thank you all for joining us. If there are any other questions that you'd like to take offline, I will stay on the call now. But other than that, thank you all for joining us for the first in the webinar. We'll be running the recording will be made available, and we will be running the same webinar again at the beginning of next year for those who couldn't make it, or if there was anyone else from your team that you think would benefit seeing this. And do watch out, throughout next year, we'll be running a regular series of webinars on different topics, including biofiltration and green infrastructure, and other in-depth technical dives into topics that we don't often get to talk about. So we'll keep you in the loop with when you can expect to see those. So in the meantime, thank you all for joining us. And if we don't get to see you before the holidays, have a good Christmas and a good holiday. And look forward to getting in touch for the next job in the new year. So thank you all, and do hope to see you again soon.
Thank you, Matt. Thank you, everybody.
Cool, thank you.
See you guys soon.
Thank you.
Thank you.
Thank you.